Alright, in this video we'll be going through the 2024 electricity exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself once you completed the question or get stuck, unpause the video to see how I go about getting the answer. Stefan's car battery recently needed replacing, so he investigated new and used batteries in different situations. His car has a new battery with an EMF of 12 volts and an internal resistance of 0.05 ohms. Explain the meaning of the term EMF. Alright, so EMF is the voltage across the terminals of a battery or a power supply when no current is flowing. And so you can write that in. Stefan observes what happens to the voltmeter reading while opening and closing the switch. Explain why the reasonings are the same or different. Values and calculations are not required. Alright, so when the switch is open, obviously that is when no current is flowing because we have an open circuit. Okay? And so therefore, the reading across the voltmeter is going to be the EMF of the battery. Okay? And so that is going to be 12 volts. However, when the switch is closed, therefore current will be flowing, and so therefore we would have current flowing through our internal resistor, okay? Again, remember our internal resistor is not a real resistor, it's not there in real life. This is just a way to quantify the resistance of the power supply and the resistance through the wires, okay? So when current flows through our internal resistor, there is obviously going to be a voltage drop, okay? And this is what we quantify as our lost volts. Alright, our lost volts, okay? And so therefore, the terminal voltage in this case is going to be equal to our EMF minus our lost volts, alright? And I know it says no calculations are required, but we can still figure out what our lost volts are going to be, and so we can figure out that terminal voltage. Again, if you're doing this question, or if you were doing this exam, you wouldn't need to do this, so you don't need to waste time, but I'm just doing it to show you for your understanding, okay? So we know that V is equal to IR, and so therefore I is equal to V all over R. We have our voltage of 12 volts divided by our resistance of 7 ohms, and this gives a current of 1.71, and so therefore the voltage drop due to our internal resistance is going to be V is equal to I little r, and so this is going to be equal to 1.71 multiplied by 0.05, and that is equal to 0.086 volts, and so therefore our terminal voltage is going to be equal to 12 minus 0.086, which is equal to 11.91 volts. There we go. And so therefore, you can see that this is less than 12 volts, alright? After long use, the internal resistance of the 12 volt battery increases to 0.5 ohms. The discharged battery is charged by a 24 volt DC power supply with a 15.5 resistor in series. Calculate the terminal voltage across the battery. Begin your answer by calculating the circuit current while it is being charged. Alright, so there are two ways of doing this. The first way is by using Kirchhoff's voltage law, or the second way is just by using V equals IR, alright? So first I'm going to use Kirchhoff's voltage law, alright? So if we start over here, we see we have a 12 volt rise, okay? So therefore we can start with 12 volts. And we're going to have a voltage drop due to this resistor, okay? And this voltage drop is going to be equal to the current multiplied by the resistance of 15.5, okay? And so we minus 15.5 I. And then we have an opposing power supply, okay? Because this is going in the opposite direction to what we are traveling in, okay? We're traveling this way, but the power supply is going in this way. And so we minus 24, and then we come up all the way over here, and we have another voltage drop due to the internal resistance. And so this is minus 0.5 I. This is all equal to 0. And so therefore negative 12 minus 16I is equal to 0. And so therefore negative 12 is equal to 16I. And so therefore negative 12 all over 16 is equal to I. And this is equal to negative 0.75 amps. And obviously the negative in this case is just saying that the current is going in opposite direction to what we decided. We decided that current is going in this direction, and so in reality current is going in this direction, alright? Another way in which we could have got the current is by calculating what's called the effective resistance. As we see, we have 12 volts coming this way, and we have 24 volts coming in the opposite direction, okay? And so therefore, the effective EMF is going to be equal to the 24 minus the 12, okay? And so therefore we have an effective EMF of 12 volts, okay? Alright? And so therefore, if we have an effective EMF of 12 volts, we can just use V is equal to IR, and therefore I is equal to our V all over our R. Our voltage in this case is now 12 volts divided by our total resistance, which is 15.5 plus 0.5, okay? So 15.5 plus 0.5, and that's obviously equal to 16. And so we have the exact same scenario that we have over here. And this gives a current of 0.75 amps. And obviously the current in this case is still going in this direction, alright? Alright, so now we want to calculate the terminal voltage across the car battery, okay? And so the terminal voltage across our car battery is going to be this voltage right over here, okay? So it's going to be the voltage between these 2 points, which as we can see is the same voltage across these 2 points right here, okay? And so therefore, this voltage, this terminal voltage, is going to be equal to our 24 volts minus the voltage drop across this resistor, so minus IR. And obviously we know that the current is equal to 0.75, and we know the resistance is equal to 15.5, okay, so we can replace that. That's equal to 0.75 multiplied by 15.5, and this gives a terminal voltage of 12.375 volts. There we go. Stefan connects a 12-volt DC power supply to a 0.14 farad capacitor, 2 lamps, and a resistor as shown below. The resistor and the lamps each have a resistance of 10 ohms. Give an in-depth explanation of what Stefan would observe by comparing the brightness of lamps A and lamp B as soon as the switch is closed and 10 seconds after the switch is closed. Alright, so as soon as the switch is closed, let's do lamp A first, okay? So lamp A initially will glow brightly. So glow bright initially, okay? And this is because current is max through here, okay? However, as charge begins to accumulate on this capacitor due to repulsive forces, current will begin to slow down, okay? So therefore less current will flow through the lamp, and as P is equal to I squared R, as our current is going down, and so therefore the power consumed by the lamp will also go down, meaning that the lamp will glow less bright. Okay, and so this will continue up until the capacitor is fully charged, and at that point, the current will stop through this branch, okay? So there will be no current flowing through this branch, and so therefore, because there's no current flowing through this branch, I will be 0, okay? And so therefore, power will be 0, and so lamp A will stop glowing, okay? However, for lamp B, in this branch, there is no capacitor, okay? But because P is equal to I squared R, because the bottom branch has a higher resistance value because there is a resistor here, the power used by lamp B will be less than lamp A, okay? And so therefore lamp B will glow less bright. However, because it does not have a capacitor in this branch, it will continue to glow even after lamp A has stopped glowing, okay? And so you can write that in words. Harry is experimenting with coils and magnets. Harry measures an average EMF of 250 microvolts that is induced in a coil when the current in it changes from 10 amps to 6 amps in 0.4 seconds. Calculate the self-inductance of the coil. Alright, so our self-inductance is our L value, okay? And we know that the EMF in the coil is equal to negative L change in current all over change in time, okay? Now for this particular case, we do not care about this negative, okay, because we're not trying to quantify the physical properties of it, we're just trying to find the magnitude of our self-inductance, okay? Remember that negative is just Lenz's law, meaning it's just saying that the EMF that the inductor produces is in opposite direction to the change that caused it, okay? And so therefore, if we're trying to find our L, we can take our EMF divided by our change in current all over change in time, okay? And this is equal to our self-inductance. And so therefore, now plugging in our numbers, we have an EMF of 250 times 10 to the negative 6, okay? And that is all over our change in current, which is from 10 minus 6, okay? So that's 4, all over our time, which is 0.4 seconds, and this gives a self-inductance of 2.5 times 10 to the negative 5 henries. There we go. The coil has 25 turns and an area of 1.6 centimeters squared. This coil is inserted into a magnetic field of flux density 1.8 Webers per meter squared, such that its plane is perpendicular to the lines of flux of the field. It takes 0.3 seconds for the coil to be placed in the magnetic field. Calculate the EMF induced in the coil. Alright, so we know our change in flux is equal to our magnetic field strength times our area. We are given the magnetic field strength right here, so that's 1.8 times our area of 1.6 times 10 to the negative 4, okay? It's given right over here. And this gives a change in flux as 2.88 times 10 to the negative 4 Webers, alright? And so we know that our EMF is equal to negative N, change in flux all over change in time, where our N is the amount of turns in the coil, and obviously the change in flux is the change in flux, and the change in time is the change in time. And so therefore, our EMF is equal to negative 25 multiplied by 2.88 times 10 to the negative 4 all over 0.3 seconds, and this gives an EMF of negative 0.024 volts. There we go. Harry then drops a bar magnet through a metal ring. Explain why its acceleration will not be equal to 9.81 meters per second. In your answer, you should include ideas about what happens when the magnet enters the ring, as well as when the magnet leaves the ring. Alright, so the overarching idea about this is that when the magnet falls through the ring, it will induce a current within the metal ring, and so therefore those currents will produce a magnetic field within the ring, and due to Lenz's law, this magnetic field will be produced in a way that will oppose the motion of the magnet, okay? And so therefore, as the magnet is moving down, the opposing magnetic force will act upwards, okay? And so therefore the net downwards force is less than that of F is equal to mg, okay? So that's the overarching idea. So as the magnet falls through the ring, the magnetic flux through the ring will increase, okay? And due to Faraday's law, this change in the magnetic flux will induce a voltage within the ring, and this induced voltage will produce a current within the ring, and this current is known as eddy currents, okay? And due to Lenz's law, the induced voltage will produce eddy currents such that the eddy currents will produce a magnetic field that will oppose the motion of the bar magnet. Okay? And so therefore the magnetic field will be produced in such a way that the magnetic force will be acting upwards. Okay? And so therefore our net downwards force is equal to our mg minus the magnetic force, which remember this is the force due to our induced magnetic field. Okay? Alright, so that's when the magnet is entering the ring, but as the magnet leaves the ring, okay, so we have our south pole here and our north pole here. As the magnet leaves the ring, we again have a change in flux. And so a lot of these same things will happen again. Because we have a change in flux, this will induce an EMF within the ring. Therefore, this induced EMF will produce eddy currents. And again, due to Lenz's law tries to oppose the change that caused it, okay? And so as the magnet is leaving now, Lenz's law will try to keep the magnet within the ring, okay? And so before, Lenz's law tried to keep the magnet out of the ring, thus producing an upwards force. However, now that we're below the ring, Lenz's law will try to keep the magnet within the ring, thus still producing an upwards force, okay? And thus, even when the magnet is trying to leave the ring, the downwards acceleration is still less than 9.81 meters per second. And so you can write that in. Harry next connects a 0.6 Henry's inductor and a lamp whose resistance is 12 ohms in series to a battery through a switch. Harry notices that the lamp takes some time to reach full brightness once the switch is closed. Calculate the current through the lamp after 0.6 seconds. Begin by calculating the time constant of the circuit. Alright, so we can calculate the time constant of the circuit by using L all over R, okay? Our inductance is equal to 0.6, so 0.6 all over our resistance of the circuit, which is 2 ohms, so divided by 2, and this is equal to 0.3 seconds. We can calculate our max current, okay? Remember, our max current is when the inductor is no longer producing a back EMF, and so therefore our inductor kinda acts like an ideal wire. And so therefore, Ohm's law just applies, and we have V all over R, where our R is equal to 2 ohms, and our V is equal to 12 volts, okay? And so this is equal to 6 amps. And so therefore, after 0.6 seconds is after 2 time constants, alright, because 0.3 times 2 is 0.6. Okay, so we can calculate our current after 1 time constant. The way we will do that, remember our graph where we have time and current here. Because this is an inductor, our current versus time graph is going to be like this, alright? And so therefore, after 1 time constant, we're going to reach to 63% of its max value. And so we can calculate after 1 time constant as 1 minus 0.37. And this gives a value of 3.78 amps. And so therefore, after 2 time constants, which is what we're trying to find, we have 0.37 squared. And this is equal to 5.18 amps. There we go. Rachel is experimenting with AC circuits. She connects a 70 millihenries inductor with a soft iron core and a 40 ohm bulb in series with a 110 volt RMS 60 Hz supply. Calculate the peak voltage of the power supply. Alright, so this is our classic question where we have V RMS is equal to V peak all over square root 2. If you want to know where this equation comes from, I go through it in my electricity playlist, so you can go check that out. But for NCEA, you don't even need to know where this equation comes from. You can just memorize it, I guess, or you don't even need to memorize it. It's on your formula sheet, so you can just use it. And so V RMS multiplied by square root 2 is equal to V peak. And so therefore our RMS voltage is 110 volts times square root 2, and that's equal to 155.56 volts. There we go. Calculate the phase difference between the supply voltage and the circuit current and state which one leads. Begin your answer by showing that the reactance of the inductor is 26.4 ohms. Alright, so we know that the reactance of the inductor is equal to omega L. We know that omega is equal to 2 pi f. We're given our frequency over here as 60 Hz, okay? And so therefore 2 pi times 60 is equal to 120 pi. We are also given our inductance over here as 70 millihenries, okay? So that is equal to 70 times 10 to the negative 3 henries, alright? And so therefore the reactance of our inductor is equal to 120 pi multiplied by 70 times 10 to the negative 3. And this is equal to 26.4 ohms. There we go. Alright, so if we use our phasor diagram, we know that the voltage across our resistor comes to the right like this. And we also know that the circuit current is in phase with the voltage across our resistor. And the voltage of our inductor leads the voltage of our resistor by 90 degrees. Alright, and so therefore if we apply vector addition to this phasor, we get that the voltage of the supply comes up like this, okay? And so as we can see, the voltage of the supply leads the current, okay, by some angle. Let's say this angle theta, okay? And so we need to find out how much the voltage of the supply leads our current, okay? And we can do that by finding this angle. And the way we would do that is by redrawing our phasor diagram. As we know, this is a series circuit, and so therefore the current at all points throughout the circuit is going to be the exact same at any given time. And so therefore, if we apply Ohm's law to this phasor diagram, we get that VL is equal to the current multiplied by the reactance of the inductor. The voltage of the supply is equal to the current multiplied by the total impedance. And the voltage of the resistor is equal to the current multiplied by the resistance value. Okay? And so because the current is the same at all points, if we just get rid of current, the shape of our phasor diagram will remain the same. However, obviously, because now we just got rid of current, the values, the magnitude of our vectors will change, but the shape itself will not change. And so if the shape gets retained, therefore this angle is preserved, okay? So our new phasor diagram will be like so, where we have our resistor over here, the reactance of our inductor, and the total impedance like so, and this is our angle theta. And our resistor is just our light bulb in this case, which has 40 ohms of resistance, okay? So this is 40 ohms. And so therefore, if we have our resistor coming over here, we have our reactance of our inductor coming over here, and our total impedance is this value right here. So this is XL, this is R. All right, and so we can find out this value theta because we know XL and we know R. Okay, and so this is the adjacent side and this is the opposite side. Okay, so theta is equal to the inverse tan of XL, which is 26.4 all over 40, and this gives a theta of 33.4 degrees. There we go. The inductor has a soft iron core. Explain what Rachel would observe in the brightness of the lamp when she slowly removes the iron core from the inductor. Alright, so we know that the iron core increases our inductance, okay? So if we remove that, therefore we're going to decrease our inductance, alright? And so as the reactance of our inductor is equal to omega L, as the frequency of our circuit has remained the same, therefore our omega will remain the same, but we've decreased our inductance, and so therefore the reactance of the inductor will decrease, as our total impedance is equal to square root XL squared plus R squared, right? Because that comes from the vector addition of our reactance and our resistance, okay? Therefore, as XL has decreased, therefore our total impedance will decrease. And as V is equal to IZ, as our voltage has remained the same, but our total impedance has decreased, therefore our current must increase, okay? And therefore as P is equal to I squared R, as the current has increased, therefore the current through the bulb has increased, therefore the power used by the bulb will also increase, and so therefore the lamp will glow brighter. Okay, and so you can write that in words. Rachel then reinserts the iron core and adds a capacitor in the circuit in order to achieve resonance. Explain why the reactance of the capacitor needs to be 26.4 ohms. Begin your answer by describing what happens at resonance. Alright, so resonance is what happens when the current in the circuit is at a maximum, okay? And so therefore, in order for current in the circuit to be a maximum whilst the voltage is remaining constant, therefore our total impedance must be at a minimum, okay, because V is equal to IZ, alright? And so therefore, remember as our total impedance is the vector addition of our phasor diagram, okay? And if we were to draw our phasor diagram now with our reactance of our capacitor, like so, the reactance of the capacitor needs to equal to 26.4 because the reactance of the inductor is also 26.4, okay? And so therefore, these two need to be equal to each other. The reason for that is because, as you can see, they're 180 degrees out of phase. And so therefore, if their magnitudes are the exact same, but their directions are opposite, therefore they're going to perfectly cancel each other out. Therefore, our phasor diagram will collapse into just our resistor, and so therefore, if we apply vector addition to the resistor and nothing else, we get that the total impedance is equal to the resistance value, okay? Another way you can look at this is by looking at the equation for our total impedance, and we get XL minus XC squared plus R squared, okay? And so if these two values are equal to each other, then this will collapse to 0, and we get Z is equal to square root R squared, and so therefore our Z is equal to R, alright? And so therefore, our reactance of our capacitor and the reactance of the inductor must be equal to each other in order for them to cancel out, and therefore making our impedance a minimum value. Therefore, as our impedance is a minimum value, our current can be at a maximum value. Alright? And so you can write that in words. And with that, we're done. See you.